Hi everyone, welcome to the third lecture of this final module on sensors for healthcare, and we are discussing the course on microsensors and nanosensors. In the previous class, we have talked about glucose sensors. We have covered a vast variety of glucose sensors, including the electrochemical and optical glucose sensors. The next in the series is the ECG sensors. ECG is very important, particularly for the measurement of heart electrical pulses. Therefore, in today's class, we are going to talk about ECG in little detail. And after that, in the next class, we will talk about some more sensors like MRI, and if time permits, we'll also talk about pulse oximeters. Okay. So before we actually discuss the ECG, we have to understand the electrical system of heart. Okay, we all know that the heart generates electricity, and it also coordinates heartbeat through cardiac conduction system. So let's try to understand the major component or the pathways of the electrical conductivity in the cardiac system. Okay. The major components of pathway of the cardiac electrical systems are the sinoatrial node, SA node, from which the electric pulse starts. Okay. The next is the atrioventricular node, which is the AV node. Okay. Then we have a bundle of His, which is kind of fiber. We'll see in a while what it is. Okay. And then this has right and left bundle branches. Then we have Purkinje fibers, and finally it goes to ventricles. Okay. So let's see all these components in very brief. Will not go more in its biological part. We are more interested in the kind of signals which is generated by these cardiac electrical systems. Okay. The SA node is basically located in the upper right atrium as shown in this figure. Okay. This node acts as a natural pacemaker, and it initiates electrical impulse. Okay. This impulse is about 60 to 100 times per minute. Okay. This electrical signal which is generated at the SO node is spread through the atria, and this causes them to contract and push the blood into the ventricles. Okay. In the series, we have another node which is the AV node. The impulse which has started at the SA node reaches the AV node, and this AV node, if you see, is found between the atria and the ventricles somewhere here. Okay. Now, when the impulse reaches the this AV node from after traveling from the SA node, okay, it is delayed for a short interval. Okay. And this delayed or this pause allow the ventricles to fill with the blood before actually they contract. Okay. This delay is very important for the effective pumping of the heart system. Okay. Now, from the AV node, the signal passes to the bundle of His. Okay. A bundle of His is nothing but a group of specialized conducting fibers. Okay. And this group of specialized conducting fibers basically originate at the AV node. Okay. And it finds its position in the interventricular septum. Okay. If you see this bundle of His, this particular system, structurally they looks like elongated cord like system which has approximate length of about 1.8 to around 2 centimeter and about 4 mm in the dia if you talk about adults. Okay. This bundle of His splits into two different bundle branches, that is the right bundle branches and the left bundle branches. Okay. And now they conduct impulses to the right and left ventricles through this right and left bundle branches. Okay. Further, these bundle branches lead to the Purkinje fibers, okay, which rapidly distribute the electrical pulses throughout the ventricles. Okay. This causes them to contract and pump blood out of the lungs and rest of the body. Okay. the entire sequence that we have just seen of electrical impulses and the muscle contraction, actually they occur very rhythmically. Okay, they have a very systematic contraction and elongation. Okay, controlling the heart rate and coordinating efficient flow is possible because of this rhythmic contraction. Okay, this rhythmic contraction, if there is any abnormality in this, okay, can suggest about the underlying heart diseases. Okay, and this is detected by the ECG sensors, which is basically the electrocardiogram sensors. Okay, so an ECG basically is an non-invasive test that records the electrical activity of the heart using electrodes which are placed on different parts of the body, including at the chest, at arms, and at both the legs. Okay, ECG graph actually display how the heart beats. It measures both the heart rate as well as its rhythm. Okay, let us try to understand that why understanding this ECG sensors is important and how this ECG sensors has become an integral part of the sensors for the healthcare. Okay, it is crucial for diagnosing a variety of heart conditions. Okay, this include irregular heart rhythms. We have just seen that ECG do not only measure the heart rate, but it also measure the rhythm of the heart. Okay, therefore it can quickly tell you about any symptom of heart attack or sign of blocked or narrowed arteries, which is basically nothing but a coronary artery disease. Okay, ECG are also used to identify causes of symptoms. For example, for a chest pain, dizziness, fatigue, or even a shortness in the breath. Okay, basically if all these symptoms is not arising from the any underlying heart conditions, okay, it can segregate non-heart and heart based diseases. Okay, so if the symptoms, like for example chest pain, is not because of any underlying condition in its heart, or it is because of any other body condition, it can quickly distinguish among them. Okay, the ECG helps monitor ongoing treatment or the function of implanted devices, say implanted device, for example a pacemaker. Okay, so it can also track the effects of heart medication. So if you are taking certain medicines for improving your heart blockage or heart pumping, okay, it can quickly tell you that if the medicine is working in a fine way or not. Okay, this ECG provides quick and vital information that can enable doctors to make rapid, accurate treatment decisions. So it can be done in a hospital or even in a ambulance. Okay, the test is pain free. It's a quick and cost effective, therefore it is accessible to even in a rural settings. Okay, so you do not have to actually go to a very high quality hospitals just for a ECG. It can be done in a rural setting also. Okay, so let us try as an electrical engineer to understand how this ECG functions. Okay, we know that it measures the electrical activity of the heart. Okay, basically this ECG has a number of electrodes, particularly 12 different electrodes are there. So in the sensors mostly we will discuss about how these electrodes can be fabricated or the placement of these electrodes. Okay, so these electrodes detect voltage changes particularly on the skin surface, because it's a non-invasive electrode placing technique, so you do not actually invade the skin. So it's basically detect voltage changes in the on the skin surface. Okay, then electrical impulses are generated by the SA node and propagate through the heart, and it is recorded as time varying voltage, which is nothing but a ECG waveform. Okay, so electrodes are placed on the skin, which pick up the bioelectrical signal which is generated by the heart. We have just seen that it starts from the SA node and goes to the AV node. Okay, the signal passes through a number of amplifier to increase its strength, and then you have filters in place which remove any noise. Okay, the ECG devices digitizes the cleaned signal from the display, and it makes it available for further analysis. Okay. So a number of electrode systems are available for ECG. You have the conventional wet AgCl electrode, which can be used for ECG monitoring. Okay. You have dry metal electrodes. Then many research group has reported the microneedle array or MAE electrodes. Nowadays ECG electrodes are also integrated in textiles. So we have textile or fabric based electrodes. Then many electrodes are coated with a number of nanoparticles, including carbon nanotube or graphene. So you have nanomaterial based electrodes, and finally, because of the advancement in the stretchable polymers, you have available tattoo based ECG electrodes. Okay. So the wet AgCl electrodes are the traditional silver chloride electrodes, which is basically standard in the clinical ECG. Okay. These are disposable and uses the conductive gel and are basically adhered to the skin surface. Okay. Dry metal electrodes are made up of metals that include gold, or even cost effective ECG are made up of stainless steel electrodes, or sometime you will also find that these dry metal electrodes are basically conductive polymer based electrodes. Okay. As the name suggests, they do not require any gel, so they offer better reusability and very low skin irritation, because you are not applying any external gel. Okay. But they may have higher motion artifacts. Okay. You have metal button electrodes or polymer based, dry contact based electrode. Okay. A number of advancement is existing in this kind of electrodes. Okay. Then we have microneedle array electrodes, MAE electrodes. Basically it uses array of microscopic needles to penetrate the skin's outer layer, which reduces the impedance and improve the signal quality. So it is, you can say that it's kind of minimally invasive technique for ECG measurement. Okay. The materials for these electrodes can be any low melting point alloys kind of material, and they can be fabricated by simple micro molding technology, or nowadays patterning is also possible of these electrodes using the simple SU8 kind of polymer, the photoresist in a photolithography laboratory also. Okay. Then we have textile or smart fabric based electrode, which integrate conductive threads or fibers into a wearable fabric, or it is done by weaving or knitting. Okay. These e-textiles allow for comfortable long-term ECG monitoring, and it is possible to integrate with the shirts, or even textile patches are also available. Okay. They are very much being investigated in the wearable health devices and for continuous ECG monitoring. Okay. So then we have nanomaterial based electrode, and the nanomaterial which is most popular for this kind of measurement are carbon nanotubes and graphene. Okay. So electrodes are made from carbon nanotubes or graphene, and they offer very high conductivity, as well as at the same time a good amount of flexibility is also provided. Okay. They can be fabricated by techniques like a simple spin coating or chemical vapor deposition, or even by the chemical bar deposition, which is CBD. Okay. They enable a high resolution in the next generation wearable devices. Okay. And nowadays these nanomaterial based electrodes are also available in the beyond this CNT or other carbon allotropes, and we have other materials like MXenes which are being investigated for these applications. Okay. Then we have tattoo based electrode, which are nothing but the conductive polymer like P.PSS, which can be printed or even transferred as ultra thin tattoo electrodes for highly conformable and unobstructive ECG patches. Okay. They can be fabricated by simple solution processing on a simple flexible substrates like polyamide or even on PET. Okay. They are transferred from these polymers or the flexible substrates onto the skin. Okay. the ultimate aim of all the electrodes that we have seen is to generate certain electrical signal, which is of great importance in the ECG. Okay, the key electrical signal in the ECG are the distinct waveforms that represent specific phases of the heart electric cycle. Okay. Each signal correspond to basically depolarization or repolarization event within the cardiac conduction system, enabling diagnosis of heart function and the rhythm. Okay. So, depolarization and repolarization are basically the central electric event in the cardiac conduction system. This drives each heartbeat into certain characteristic rhythm. So, if you see depolarization, it has to be understood based on certain charges. Okay. So, before we actually understand the charge state of the heart, we have to understand that at rest the heart cells are basically polarized. Okay, and this polarization is with a negative charge inside and positive charge outside. Okay, so inside this heart cells you have a negative charge and outside it is positive, and that's how we are calling it polarized even at rest state. And with respect to this we have terms like depolarization and repolarization. Okay, so let us quickly understand what I mean by depolarization and what do we mean by the repolarization. Okay, so depolarization occurs when an electrical impulse from the SA node to the neighboring cells causes sodium ions to rapidly flow into heart muscle cells. Okay, so what you are doing basically, you are pumping sodium ion, which is basically a positive ion, inside the heart cells. Okay, so this make the inside temporarily positive, or if you remember, if we have assume that inside it is already negative, so we can say that it is less negative. Okay, so either you can understand it by thinking that we are making inside more positive or less negative. Okay, now this positive change triggers the contraction of the heart muscle. Okay, so depolarization moves as a wave from cell to cell, atria first, then ventricles, which ensure a orderly pumping. Okay, then we have repolarization. So after depolarization, heart cell must return to their resting, and the resting was inside negative and outside positive. Okay, so basically if the heart wants to come to its natural state, it has to be basically in a negatively charged state. Okay, so repolarization is the process where potassium ion, which is again a positive ion, exits the cell, restoring the negative internal charge. So it exit from inside and then you have restored the negative charge. Okay, so this is kind of reset, and this reset allows the muscle to relax and be ready for the next beat. Okay, so in the cardiac cycle, the atrial depolarization starts at the SA node and spread through the atria, producing the P wave on the ECG. This P wave is very important, and we have just known that one of the wave that is generated by a heart is a P wave. Similarly, we will also see that there are other waves which are generated by the heart. Okay, the signal we have already seen that which starts at SA node, come to AV node, and then signal is paused. Okay, the signal pauses at the AV node, then travels via the bundle of Higgs and the Purkinje fibers for ventricular depolarization, which is shown by the QRS complex on the ECG. So another kind of wave that is available in the ECG is a QRS complex wave. Okay, we'll see on a ECG that how a QRS complex wave looks like. Okay, this is about depolarization. Then we have repolarization. So on the ECG data, okay, the ventricular repolarization is represented by the T wave. So two waves we have seen, a P wave, QRS wave, right, or QRS complex wave, and then third type of wave is the T wave. So the two P wave and QRS complex wave is during depolarization, and during the repolarization it is the T wave. Sometimes there are some U waves also. We'll see what is that U wave, but that is not a regular wave. Okay. Then the atrial repolarization is hidden within the QRS complex wave and is not individually visible. Okay. So, if you compare this depolarization and repolarization, repolarization is basically slower, okay, and does not use the fast conducting pathways, okay, and rely on the cell to cell conduction, which is why the T wave is longer in duration than the QRS complex wave. Okay. So, if you see the sequence, depolarization, which is contraction, and it triggers the pumping of the blood, and then you have repolarization, which is basically the relaxation and prepares the heart for the next cycle. Okay. So, both phases together generate the electrical activity which is detected by the ECG. Okay. So, we will see what is P wave, QRS complex and T wave. Right now we have seen till now that P wave is the atrial depolarization, QRS complex is the ventricular depolarization, T wave is the ventricular repolarization. Okay. And disruption to any of this event can lead to imbalance in the cardiac system. We will see what can be imbalances can be found. Okay. So, from this discussion we have seen that the key electrical signal in the ECG are the P wave, QRS complex and T wave. 2 from depolarization and 1 from repolarization, and occasionally we have also thought that there are certain U waves. Okay. So, P waves, we already understand that what are P waves. It represent the atrial depolarization, which is the electrical activation which is causing atria to contract and push blood into the ventricles. Okay. And abnormalities in this P wave can indicate a number of heart conditions, including the conduction blocks. Okay. Then the QRS complex wave, we have seen that it reflects the ventricular depolarization, signaling the rapid activation and contraction of the ventricles as they pump blood to the lungs and the rest of the body. Okay. And the width and shape of this QRS complex signal helps in detecting bundle branch blocks, ventricular hypertrophy or the presence of the ectopic ventricular beats. Okay. Then we have T waves which marks the ventricular repolarization, similar to the QRS complex which marks the ventricular depolarization. This T wave marks the ventricular repolarization as the ventricles recover electrically in preparation for the next heartbeat. Okay. It prepares for the next heart cycle. Okay. Abnormal T wave morphology can indicate electrolyte disturbances and ischemia in the heart. Okay. Which is basically different heart conditions. Okay. Then you have U wave, which is occasional. Okay. And sometime it is seen at the T wave and sometime it is mixed with T wave. So, it is very difficult to identify. Okay. And its origin is not fully understood and can be linked to the after potential in the ventricles. Okay. And the prominent U waves can reflect again different cardiac pathological conditions. Okay. So, let us quickly see ECG signal. Okay. And this is the area of the P wave. Okay. After that you have different segments. We will see what are the segments. You have ST, QT, RR, different segments. Okay. And then this part is the QRS complex. Okay. So, along with these waves you have different intervals and segments between two different waves. Okay. So, we will see what are those segments. Okay. So, in ECG several key intervals and segment reflect the electrical activity of the heart during each cardiac cycle. Okay. And understanding these is crucial for diagnosis cardiac abnormalities. Okay. Let us see what are the different segments which is possible. We will not cover all the segments, but we will try to see some of the intervals. Okay. For example, if you talk PR interval. Okay. PR interval is around of duration 0.12 to 0.2 seconds in a adult. Okay, and this is the time from the atrial depolarization onset to ventricular depolarization onset. Means that it start of this PR interval takes care from the start of the P wave to the start of the QRS wave. Okay, and if this PR interval is larger, it suggests a first degree AV blockage. Okay, a short interval of this PR, short interval means anything around 0.1, okay, or 0.09 second, okay, and the prolonged interval means anything greater than 0.2 seconds. Okay, again it has to be calibrated to the patient. Okay, so a short interval of this PR interval time frame indicate the pre-excitation syndromes. Okay, then you have the QT interval, which is usually larger as compared to the PR interval, because we have already seen that in the discussion of the electrical pulses. So the normal interval for this QT is around 0.35 to 0.44. Okay, and this take cares the total duration of the ventricular depolarization and the repolarization, means the start of the QRS to the end of the T wave. Okay, and the prolonged QT, this QT interval can predispose to the dangerous of the heart conditions like arrhythmias. Okay, there are other health conditions also which arises from other segments like ST segment, TP segment, or even with the RR interval as well as with the PP interval. As the name suggests, PP interval is nothing but the time between two successive P waves. Okay, so this is a list of different heart conditions for this different segments, and based on this the ECG signal analysis is done. Okay, so that's how quick analysis of your ECG can be done by doctors by taking into consideration of this normal duration for different segments and different intervals, and then comparing that normal conditions with your ECG data. Okay, and based on that the conclusion can be quickly drawn. Okay, so this is a very good non-invasive technique to comment on the heart conditions. Okay, and thanks to the electrical pulses or electrical waves basically which is generated by the different state of the heart. Okay, so there are a number of advantages which are associated with the ECG signals or ECG sensors, like it is a very simple device. Non-invasive means painless device. Okay, that usually takes only a few minutes to record the heart's electrical activity. This ECG helps detecting the abnormal heart rhythms, heart attack conditions. If any poor blood supply condition is there, it also talk about that. Any kind of other cardiac disorder, it takes care of all of these, but it do not get any interferences with any non-heart conditions, because it solely take care only of the electrical conditions. Okay, so it is useful for monitoring the effectiveness of treatments, for example the medications for the heart, or the implanted pacemakers, as well as it also track the heart conditions over a time. Okay, so ECG is often one of the first tests which is used in the emergency situation, for example in abnormal chest pains, to quickly assess the heart function, and it guided to the treatment. Okay, if it is non-heart diseases, it can at least segregate between the two. Okay, so in the next class we will talk about the MRI and the pulse oximeters. Then in the final lecture we will try to summarize the complete course on microsensors and nanosensors, and we will try to see that what is the outcome of this course and what we have learnt in this 60 lectures. Okay, thank you.